So this is the question I would like to discuss. And this is, of course, one of the most basic questions of cosmology, whether or not the universe had a beginning. And
too many people mistakenly equate knowledge with certainty. When they say that we do not know that the universe began to exist, what they really mean is that we are not certain that the universe began to exist. But of course, certainty is not the relevant standard here. The question is whether 2 is more plausible in light of the evidence than it's contradictory. Professor Carroll reminds us, science isn't in the business of proving things. Rather, science judges the merits of competing models in terms of their simplicity, clarity, comprehensiveness, and fit to the data. Unsuccessful theories are never disproven, as we can always concoct elaborate schemes to save the phenomena. They just fade away as better theories gain acceptance. Science cannot force you to accept the beginning of the universe. You can always concoct elaborate schemes to explain away the evidence. But those schemes will not fare well in displaying the aforementioned scientific virtues. Even many who have expressed skepticism about premise 2 admit that it is more plausibly true than not. For example, in my recent dialogue with Lawrence Krauss, he volunteered, "I bet our universe had a beginning, but I am not certain of it. Based on the physics that I know, I'd say it is a more likely possibility."
If you ask me what would I bet our universe had a beginning.
You'd bet what?
I'd bet our universe had a beginning, but I'm not certain of it.
Well,
and I know that the physics.
certain.
Hold on, that is my based on what the physics that I know. I'd say it's a more likely possibility.
Yeah, right.
But it doesn't say the universe had a beginning. It says it's likely.
This is to admit precisely what cosmologists like Alexander Vilenkin have contended all along, that the evidence makes it more likely than not that the universe began to exist. Consider first evidence from the expansion of the universe. The standard Big Bang cosmogonic model implies that the universe is not infinite in the past, but had an absolute beginning a finite time ago. Although advances in astrophysical cosmology have forced various revisions in the standard model, nothing has called into question its fundamental prediction of the finitude of the past and the beginning of the universe. Indeed, as James Sinclair has shown, the history of 20th century cosmogony has seen a parade of failed theories trying to avert the absolute beginning predicted by the standard model. Meanwhile, a series of remarkable singularity theorems has increasingly tightened the loop around empirically tenable cosmogonic models by showing that under more and more generalized conditions, a beginning is inevitable. In 2003, Arvin Bord, Alan Guth, and Alexander Vilenkin were able to show that any universe, which is on average in a state of cosmic expansion throughout its history, cannot be infinite in the past, but must have a beginning.
So this kinematic incompleteness theorem that I proved with Arvin Bord, Alan Guth several years ago, very loosely stated, it says the following, that a space-time that is on average expanding, that is the average Hubble rate, is positive, is past-geodesically incomplete. I will give a more accurate statement in a moment. But the important thing about this theorem is that it is a purely geometric theorem. It doesn't assume any dynamics. That is, it doesn't rely on Einstein's equations. You could have some other theory based on some other equations. It also doesn't assume any energy conditions. Actually, both Alan and I mentioned this theorem when we were here 10 years ago at Stephen's 60th birthday.
In 2012, Vilenkin showed that cosmogonic models, which do not fall under this condition, including Professor Carroll's own model, fail on other grounds to avert the beginning of the universe.
And I will, to lift the suspense, I'll tell you my conclusion right away, that basically none of these approaches work. None of these approaches to try to avoid the beginning of the universe is successful, at least so far.
Vilenkin concluded none of these scenarios can actually be past eternal. All the evidence we have says that the universe had a beginning.
So the corollary is that inflating spacetimes must be past-geodesically incomplete, because inflation certainly is associated with expansion of the universe. And if the universe, so if you have this point in an inflating region, all the space-time to the past must also be inflating. And that indicates that inflationary universe must have a beginning.
The Born-Guth-Vilenkin theorem proves that classical space-time, under a single, very general condition, cannot be extended to past infinity, but must reach a boundary at some time in the finite past. Now, either there was something on the other side of that boundary or not. If not, then that boundary is the beginning of the universe. If there was something on the other side, then it will be a non-classical region, described by the yet-to-be-discovered theory of quantum gravity. In that case, Vilenkin says, it will be the beginning of the universe. Think about it. If there is such a non-classical region, then it is not past eternal in the classical sense. But neither can it exist literally, timelessly, akin to the way in which philosophers consider abstract objects to be timeless, or theologians take God to be timeless. For this region is in a state of constant flux, which, given the indiscernibility of identicals, is sufficient for time. So even if time as defined in classical physics does not exist at such an era, some sort of time would. But if the quantum gravity era is temporal, it cannot be extended infinitely in time. For such a quantum state is not stable, and so would either produce the universe from eternity past or not at all. As Anthony Aguirre and John Kihayas argue, it is very difficult to devise a system, especially a quantum one, that does nothing forever, then evolves. A truly stationary or periodic quantum state, which would last forever, would never evolve, whereas one with any instability will not endure for an indefinite time. Hence, the quantum gravity era would itself have to have had a beginning in order to explain why it transitioned just some 13 billion years ago into classical time and space. Hence, whether at the boundary or at the quantum gravity regime, the universe probably began to exist. Consider now the evidence of thermodynamics. According to the second law of thermodynamics, entropy in a closed system almost never decreases. Given the naturalistic assumption that the universe is a closed system, the second law implies that given enough time, the universe will come to a state of thermodynamic heat death, whether cold or hot. Given that the universe will expand forever, it may never reach a state of equilibrium, but will grow increasingly cold, dark, dilute, and dead. But then the obvious question arises. Why, if the universe has existed forever, is it not now in a cold, dark, dilute, and lifeless state? P.C.W. Davies gives the obvious answer. The universe can't have existed forever. We know there must have been an absolute beginning a finite time ago. The universe's energy, says Davies, was simply put in at the creation as an initial condition. Skeptics might hope that quantum cosmology might serve to avert the implications of the second law of thermodynamics. But now, a new singularity theorem formulated by Aaron Wall seems to close the door on that possibility. Wall shows that given the validity of the generalized second law of thermodynamics in quantum cosmology, the universe must have begun to exist, unless, as in Professor Carroll's model, one postulates a reversal of the arrow of time at some point in the past, which, he rightly observes, involves a thermodynamic beginning in time, which would seem to raise the same sorts of philosophical questions that any other sort of beginning in time would. Wall reports that his results require only certain basic concepts so that it is reasonable to believe that the results will hold in a complete theory of quantum gravity. Thus, we have good evidence, both from the expansion of the universe and from the second law of thermodynamics, that the universe is not past eternal, but had a temporal beginning.
What you should be doing is trying to build models, like I said. So the question is, are there realistic models of eternal cosmologies? Well, I spent half an hour on the internet. I was able to come up with about 17 different plausible-looking models of eternal cosmologies. I do not claim that any of these is the right answer. We're nowhere near the right answer yet. But you can come up with objections to every one of these models. You cannot say that they are not eternal. There's a theorem, Bordet-Guth and Vilenkin, that has assumptions, so if you violate those assumptions, you can violate the theorem.
Well, it's certainly true that such models exist, but the problem is none of them is successful. Slide 32, please. As Jim Sinclair has shown in our article in the Blackwell Companion, all of the models that Dr. Carroll has mentioned have been shown to be either untenable or not to avert the beginning of the universe. Alex Vilenkin says flatly, there are no models at this time that give a satisfactory model for a universe without a beginning.
So, getting back to the question I asked at the beginning, whether did the universe have a beginning, my answer is probably yes. For all we know, there are no models at this time that provide a satisfactory model of universe without a beginning. Inflationary spacetimes are past incomplete. Cyclic spacetimes are either incomplete or lead to thermal death of the universe if you have oscillatory behavior. And emergent universe models suffer from quantum instability.
Okay, let's talk cosmology for a minute here. Why does the multiverse need an absolute beginning? Why can it not be just simply eternal?
The reason the multiverse can't be beginningless or eternal in the past is that the Bordet-Guth-Vilenkin theorem applies to it as well as to our mini-universe within it. Any universe that is in a state of cosmic expansion, on average, over its history, cannot be past eternal. And that is true of the multiverse as well. It is true that it is in a state of expansion, on average, over its past history. And so that can't be extrapolated to past infinity. And that's why, remarkably, this amazing theorem shows that even trying to resort to the multiverse to escape the beginning of the universe won't work. And by the way, if people are interested, that lecture that Vilenkin gave at the conference in Cambridge last April, celebrating Hawking's 70th birthday, is on YouTube. If you just go to YouTube and type in Alexander Vilenkin, it'll bring up that lecture at Cambridge, and it is very accessible. It is a wonderful lecture that I think lay people can understand. It has PowerPoints that accompany it. So you can actually go and hear that lecture himself, in which he surveys contemporary cosmologies, including these multiverse models that try to avert the beginning of the universe and shows how they fail.